Hey, howdy everyone. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and this is part of my continuing lecture series on machine learning with some focus on subsurface and spatial problems. We have covered a lot of prerequisites, we've covered inferential methods, and we've just started into some more simple type of machine learning predictive methodologies. So we'll cover k-nearest neighbor during this set of lectures. I'll break it up into small pieces. There'll be a variety of different topics we want to get into today. So what's the motivation? Why do we want to get into this idea of k-nearest neighbors? What's the benefit for it? Well, first of all, it's a simple and interpretable type of predictive model. And that's good. We want to start with these simple methodologies to build up concepts. So by the time we get into ensemble and neural nets, we're going to have a strong foundation. We got to walk before we run. Instance-based lazy learning. I think it'll be kind of cool to get into that and explain that. And also, it gives us a good linkage to variance and bias trade-off. We will have a hyperparameter to work with. Now, I should say it's not really our first hyperparameter because we had the lambda in the case of the lasso and the ridge regression previously. But you'll see it's closer tied to the idea of model complexity, and I think that's very beautiful. Very flexible, performs well in many situations. Actually isn't a bad method. So let's go ahead and get into the whole idea of k-nearest neighbors. Now I think a good way to think about k-nearest neighbors is to introduce the idea of mapping in feature space. So we could imagine that we have predictor feature 1, predictor feature number 2 here, and we have our training data shown just as red dots. Now, we could have color-coded them based on their magnitudes for the response feature that we're trying to predict, but I just put red dots here. And so we could imagine that what we want to do with our model is we want to make predictions at unsampled locations. Now, when you step back and think about this problem, it actually looks very much like a geostatistical problem of trying to formulate a spatial estimator. Instead of having space, Euclidean space, some type of x, y, north, easting, and so forth, now we're dealing with a predictor feature space as we have before with cluster analysis and other types of methodologies. And so we want to formulate a model to make predictions away from the training data. And so how could we do that? Now we could use some type of parametric form, and we already covered the idea of linear regression. Effectively what we were doing was fitting a plane or a hyperplane to the training data so that at all locations I could project the combination of predictor features onto the hyperplane and say, all right, what is the response feature? And to be defined based on an equation like this, some type of sum of linear weights or slope components being applied to all of the predictor features and an intercept term. And we would get a parametric model that would allow us to make predictions. In fact, mapping between all of the training data and being able to make predictions. So parametric models, if you recall, we've shown this slide a couple of times before. You make an assumption about the functional form or shape. You're going to gain a lot of simplicity and the advantage of only having to work with a few parameters. That means that in general, the model is going to be compact and portable and easier to train. You won't require as much data to be able to train it. I have an example linear model shown here like the one on the previous slide. But the problem with parametric forms is that there's always sometimes a pretty serious risk that your estimation of this function, that parametric form you've chosen, is a poor model relative to the phenomenon that you're trying to predict. In other words, you're using a linear model like a plane or hyperplane to predict a phenomenon that doesn't behave like a plane. It's much more complicated and nonlinear in its behavior. Now, a nonparametric method makes no assumption about the functional form or shape. It's much more flexible to fit a variety of different natural phenomena. They're the intrinsic function that we're trying to estimate, f hat being our estimate. There's less risk that f hat is a poor fit for the actual best function that could represent that natural phenomena. Typically, it needs a lot more data in order to get an accurate estimate of the function. And the way I like to tell the students is that nonparametric is actually parametric rich. In other words, we go back to concepts of statistics and degrees of freedom and assumptions we have to make in the model. Often we'll find we need much more data in order to be able to predict those features. So we could imagine ourselves doing some type of non-parametric. I introduced the idea of just fitting a plane, which effectively was just linear regression. And we could try to interpolate the response features in the predictor space. And so this would be analogous to some idea, some concept of geostatistical interpolation, some type of contouring, and we'll show here kind of somewhat related to convolutional methods, inverse distance, and so forth. Let's do a quick refresh on the idea of hyperparameter tuning, because as I mentioned here, we're going to have a really nice, clean hyperparameter we can work with that'll directly control the fit, overfit, and underfit of our model. And I think that's going to be very cool. So let's remind ourselves about this. In the purpose of prediction, what we're trying to do is we're trying to get the most accurate estimates of y hat, the response features from the predictor features. We're trying to get a good estimate of that function in order to maximize the accuracy of our predictions of the response. Remember, once again, predictive statistics is all about the idea you make assumptions about the system, build a model, and then you predict or forecast the samples that will come from that system. Now, we're concerned about the accuracy of our model, and we've already talked about this a bunch of times, that we'll generally consider some type of a L2 norm. We've gone more into norms now, so a squared statistic of error. Here's the error right here, the actual training values of the response feature and the predictions directly from our model. We're squaring them, we're taking a sum of the squares, and by taking 1 over n, we're getting the mean sum of the squares, or mean squared error. Now, that's all fine and good to get the error at the training data locations, but what we really want to know is the expectation of this squared error over the testing. In other words, data not used in order to build the model. And that's a much fairer assessment of the performance of our model moving forward. That's how we find value. Now, let's remind ourselves of this idea here, that if we take that quadratic, that expectation of the testing error, and we expand it out, we've got 3 components that are additive: model variance, model bias, and irreducible error. Now, we've covered this a bunch of times, but just to remind ourselves, the variance-bias trade-off relates to this fundamental idea: low complexity models to high complexity models. Low complexity models will tend to have high model bias, but will have low model variance. High complexity models will have high model variance and low model bias. And by tuning a hyperparameter that controls the degree of model complexity, we can benefit from this bias variance trade-off, and when we add them together, we can find an optimum degree of complexity. And that's what our hyperparameter here is going to help us do. Now, just to remind ourselves the difference between a hyperparameter and a parameter. The parameters are going to be set given the degree of complexity of the model. They're going to be trained to maximize the accuracy with regard to the training data. So we'll change those parameters. In the case of this third order polynomial, we'll have b3, b2, b1, and a constant. Maybe we could call it b0 too. And we could just change those parameters to shift the model up and down, change its fundamental, local curvature, but we're still limited to a third order description. Now, model hyperparameter, this is your opportunity to tune the complexity of the model. The choice between a third order, second order, seventh order, or in this case, first order here, and a third order, fifth order, and seventh order would be the choice. That would be the hyperparameter with this polynomial model. And what we can see immediately, that if we were to tune the hyperparameter just with the training data alone, we would make the choice to go to the most complicated, most flexible model every time, because that would reduce the error, as you can see, down to 0 here, and that would be clearly overfit, not a good predictive model. And so what we have to do is we have to do some form of training and testing workflow where we're going to separate our data into training and testing data. We train the model parameters to maximize the accuracy. And at this stage, we'll train a set of models of variable complexity, and then we'll select or tune the parameters that control complexity based on optimizing that complexity with regard to match or accuracy with the testing data. That protects us to some degree from overfit. Given that quick recap, let's go back to k-nearest neighbor and let's propose a methodology, going back to what we talked about before, of mapping or interpolating the response within the predictor feature space. Okay, so what would be the possible methods? I already suggested we could use geostatistical type of methods. So we could Krieg, we could do Krieging in a high dimensional space. We do have models like the spherical, which can be spherical variogram model, positive definite model that can be extended to higher dimensions. We could perform Krieging in a high dimensional space. We could do inverse distance weighting. That would be pretty straightforward. We've already done a bunch of distance calculations in higher dimensional space. We know how to do that. Or we could do some type of moving window average, a convolutional type method. And so let's go ahead and do a convolutional method for this interpolation. What's the whole idea of convolution? Pretty straightforward, in fact. One interpretation would be that you're using a weighting function, f, and you're going to apply it to calculate a weighted average of a specific function, g. So the convolution of f over g is going to be the integration from negative infinity to infinity of the weighting function effectively over a delta window over this function x, and we're going to move that weighting function along and apply it at different centered locations on x. Now this integration is easy to extend to multi-dimensions. You could imagine a convolution of f over g with the x, y, and z, or any number of dimensions is of course possible. Now let me just sketch out a very simple description to help you understand convolution. When I think of convolution, I think of a moving window averaging type of methodology. So let's give ourselves an exhaustive function g, and we'll apply a weighting window f over this window size. And now what we can do is we can imagine positioning that window across the function and using it as a weight to the local neighborhood values from this continuous exhaustive function. If we were to apply it, it would be like provide a low-pass filter effectively. We would get a smooth version of the function. This would be an example of convolution. Pretty straightforward, a uniform weighting window being applied to an exhaustive data set. But what's our problem? We don't have the exhaustive function. We have sparse samples in general. And if we apply a uniform window, what's going to happen is this value here is pretty high. It's isolated and high. And as the window moves across and we drop that value, it would cause a jump down. That uniform weighting would result in discontinuities in the function. And so this could be a concern for the purpose of making interpolations. And so we could change from a uniform weighting. The function itself, the f of delta, could in fact be something smoother. It could have, in this case, it's very simple, triangular type of shape, where the weights would be a function, a linear function of the distance away from the centroid of the template. And the result would be that as we scan across with that weighting window, that we would, this value here that's very high, if we were over here with the weighting window, we would just start to add it, and it would have very little weight. And then as we go further, and as we get here, making the estimate of the convolution at this location right here, it would have maximum weight. As we continue to move across, it would get diminished weight, less weight, and it would drop off slowly and disappear, get zero weight, and then we'd move on. That would prevent these discontinuities, and we get a nice behavior in our convolution as shown right here. Okay, so I hope this has introduced the idea of doing convolution and making a choice between different weighting functions f, uniform, and some type of distance-based weighting. We'll have that choice when we do nearest neighbor. Now with nearest neighbor, we're going to be working with distances within the feature space. So the problem of getting everything on an equal playing field is a problem. Now getting all the features, predictor features on equal playing field is a problem again. And so we'll perform normalization or standardization. Problem is this, If we're working with acoustic impedance, which goes from 2000 to 6000, excuse me, this should probably be 10 to the third power here. But if we're working across that scale versus porosity fraction going from 0.12 to 0.28, these distances are going to seem very close. In fact, if you think about it, this problem is collapsed to almost a one-dimensional problem as far as finding distances. This axis basically does not matter. So we'll do some type of, here's an min-max normalization where 0 to 1 now for this feature and 0 to 1 for porosity normalized. And now we can see that in any direction, if we have the same length of vector, it would be the same distance resulting. Why do we want to do that? Well, here's a result from a k nearest neighbors approach for calculating the estimates for across the predictor features, porosity and brittleness. In the first example here, we have standardized each of them. So they have a mean of 0, a variance of 1, and you can see that. You can see they're going from about -4 to +4. You'd expect that. And you can see we get isotropic type of features. Now, look what happens when we go to brittleness from 0 to 100 and porosity from about 0 to about 30 almost. That range isn't too dissimilar. The variance isn't that dissimilar, but look at the striations. You see these striations away from the data? Those are being caused by the differences between the variances or ranges between the features. Now let's make it more extreme. Let's make a very arbitrary decision simply to change the porosity from percentage to a fractional porosity, and the result is you get these extreme striations. We want to remove that. That's why we do standardization. This would not be a good estimator. In fact, if you think about it, this estimator is effectively collapsed down to an estimator only considering brittleness, really. It's collapsed to a one-dimensional problem, and that's not going to be very, very useful to us. Okay, so what are we going to do with k nearest neighbors? We put all the pieces together. We've discussed standardization and normalization now. So we should be ready to just go ahead and do it. And so what are we going to do? We're going to get a nearest neighbor regression with a moving window average or convolution. Our hyperparameter is going to be k nearest neighbors. Kind of spoiler alert, eh? We said k nearest neighbors at the beginning, but that's the idea. The hyperparameter is k. And so this is very interesting. We are not using a specific radius of the window. We're using k nearest neighbors, which means the size of the window and is going to basically change based on how many data we have around us. It's going to be locally adaptive. And so in this area right here, we could suggest to estimate at this center of this circle, our window, we have sparser data, and so we have to go further away. We're using a larger window. Here, maybe we could say we have denser data and we don't have to go as far away. And so we're using a smaller window. Now, this is interesting. So it means technically our model where we have more data will be more specific, where we have less data will be more general or more smooth. So that's kind of cool. That's cool. So sparse sampled data will require a larger window. Larger K results in a smoother result. Now this is cool. So if you use a very big K, you're going to be averaging a lot of neighbor data, and the result is the entire surface becomes very smooth. That will tend towards underfit. Smaller K results in more detailed response, the prediction of the response, and we could become overfit. Now let's just to kind of solidify the idea of convolution, what a convolutional model looks like. Here's an example right here. So we have a one-dimensional data set, depth versus porosity. These could be well logs where we have some core samples sampled at different locations, irregular intervals, and we've measured from maybe core plugs the porosity and we plotted them on the depth along on the scale. And so we could go ahead and perform a convolutional based interpolation. The first example here is with a 3-meter window. Here's the next example here with the 6-meter window, and this has a 20-meter window. Now, if we made the window very large relative to the extent of the data, we would estimate for the uniform weighting approach of convolution with the average of the entire data set. So you can get an idea right here of what these estimators look like. The thing that's interesting is they are not necessarily exact estimators. They don't give us necessarily the value of the training data at the training data locations. That's an important concept right there. This is more coincidental that we're lining up perfectly. But in the case where we have a very large window of uniform weighting, there's no reason we get the data values back at their locations. So that's interesting. This is interesting, observed convolution. Okay, so now I should mention the fact that for hyperparameters, we do make a choice about k, but we also have a choice about the parametric forms available for weighting the function. We could have uniform, which I showed before when I was introducing the idea of convolution. It's insensitive to the distance of the training data to the location in the feature space at which you're estimating. Inverse distance is commonly used. It's by default, we can use it right in scikit-learn. And where we specify a power. Now, we've already talked about inverse distance in this course, so I'm not going to go into details about it. But if you look in our previous lectures, specifically in the case of cluster analysis, I believe we brought it up there to calculate a distance metric. Now, there's another important concept here. And if you step back and you wonder, okay, we've already explained how to build the model. What is the model? What actually is the model in the case of k nearest neighbors? And so the point I'd make right now is that it is a lazy model. It's lazy learning. And what that means is the model is a generalization of the training data, yes. Calculation of the actual response prediction is really delayed until you query the model, until you actually ask the model for an answer. In fact, what is the model? The model is the training data in the predictor feature space and the selected hyperparameters that tells us how to make the local estimates. We don't calculate the entire response and then use that model. We actually have to go back to the training data every time. And that's why we call it lazy learning. We've delayed the actual calculation until every time you ask the model, what's the answer? You got to keep all of the training data with you. Eager learning would be like when we talked about regression. We had that step. We showed the derivation up front. We take the training data. We build the model. So we construct the model. And then what we're able to do is then we apply queries to the model. We don't have to go back to the training data anymore. And so we say the model is input independent after the parameters are trained and the hyperparameters are tuned. But this is not eager learning. This is lazy learning. We're going to be lazy in our learning, which is kind of cool. We're greedy in our descents. We're lazy in our learning. Doesn't sound like we have great characteristics, does it? Okay, it's also instance-based learning. And there's a little bit of nuance here. We can also call this memory-based learning. And so what that means is we're comparing new prediction problems. So we have predictor feature 1 and 2. We have all of our training data. And then we'll get a new case. We have a new predictor feature value number for 1, predictor feature value for feature 2, and we want to make a prediction at a location. So we're going to make comparisons to the available training to make that prediction. That's instance-based learning. The model requires access to the training data. The training data is acting like a library of observations that we're drawing knowledge from. Predictions are directly from the training data, and we should mention that prediction complexity grows with the number of training data that we have. And this will come up again and again. This means that more training data, every single time we query the model, it's going to cost more in order to make that prediction. So this is a good time to stop. And I will get into a short discussion around computational complexity. Then I'll talk about more details around k nearest neighbors, methodologies for speedups, and also show an example. So I'll stop the video right now. I hope this initial introduction to k nearest neighbors has been useful to you. My name is Michael Pyrcz. I'm an associate professor at University of Texas at Austin. And I teach and conduct research with my team of PhD students, master students in the area of data analytics, geostatistics, and machine learning. I'm happy to discuss anytime, and I sincerely hope that this video has been useful to you. All right, take care.